Okay, today's lesson is on conditional probability. Learning intentions today to know what conditional probability is and how to calculate it, to know what independent events and dependent events are and the rules for those. Alright, conditional probability questions. They usually have two events, and you are usually asked to find the probability of one event knowing the outcomes of the other one. And the words that tell you that it is a conditional probability question is usually the question will say given. All right, that's your tell that it's a conditional probability question, given or if then. All right, conditional probability. Conditional probability is written in maths like this. So probability of A given B. So that little hat, what is it? It's a pipe. That little pipe means given. So that is read as the probability of A given B. And a good way to think about conditional probability is that it reduces the sample space. So if we had to calculate the probability of A from the Venn diagram I have here, probability of A is the outcomes in A, so that's the 20 and the 10, that's 30, divided by the total number of outcomes. So that is 100. 3 on 10. All right, if we have to calculate the probability of A given B, we have a reduced sample space now. So we don't care about these other things out here. None of this is relevant. The only stuff that counts anymore is in the circle B, which means our denominator now is the stuff in the circle B. That's the 10 and the 30, so 40. And the A is now only what's available in the intersection there. That's the A. So we now have 10 out of 40, a quarter. All right, so that's a way of thinking about the sample space, and that's what we see in the formula up here. Probability of B is the denominator, because given B is, we're only interested in the stuff inside B, and the intersection between A and B gets us the stuff that's still in A. The probability of one event affects the probability of the next event. And so these are the classic without replacement events. So selecting two cards from a deck of cards without replacing in between, that's a dependent event. Or something, could be something like being vaccinated and dying from COVID. So whether you're vaccinated or not affects the probability of whether you will die or not. All right, so they're dependent events. If we take our probability rule from the previous slide and we multiply both sides by the probability of B, all right, we get this, what is called a multiplication rule. So the intersection of A and B is equal to probability of A given B times the probability of B. And we can use this rule to test whether two events are dependent or not. Independent events. This is where the probability of each event has nothing to do with the other event. So these are the classic with replacement events. So now if I'm selecting two cards from a deck, I replace the card after selecting the first one, so that when I select the second card, the probability is the same. It's not affected. All right, or two things that are completely unrelated, like tossing a coin and rolling a die. Okay, so the probability of B does not affect the probability of A. And in maths, the way we would write that is the probability of A given B, is just the same as the probability of A. Also, the probability of B given A is just the same as the probability of B. All right, so they're independent events. If we take our multiplication rule from the previous slide, we had a given B in the formula. Now we don't need that anymore because the probability of A is just the probability of A. And so our rule simplifies to this. The probability of the intersection of A and B is just achieved by multiplying the probabilities of A and B together. And you can see that on a tree diagram. So if I have A and not A, and B and not B, if I want the probability of A intersecting B, you can just get that by multiplying along the tree diagram. All right, the other thing we'll be interested in is adding up probabilities. So if we want the total probability of A, and we only have the probabilities of A given B, we can find the probability of A by adding the other two options up. So if we have the probability of A is equal to the probability of A if B happened, and it's also equal to the probability of A if B didn't happen. So that's a total law of probabilities. All right, so we have our example here. Take a minute and read the question. Okay, so we have 3 kids doing dishes, and we note that the probability of them breaking dishes changes depending on who is doing the dishwashing. So that means it's a dependent event, and we're being asked to find the probability that at least one dish is broken. So we're being asked to find a total probability there. And then B, given that at least one dish is broken. So this is a conditional probability. So we have, in this example, this is a dependent. We're trying to find a total, and it's conditional. All right, so I have a tree diagram here ready to go. You can see the probabilities of each child washing dishes. So Adrian, 0.4, and 30% for the other two, so 0.3 and 0.3, and that adds up to 0.1, so that checks out. We have Adrian 0.01, 0.01, and then that's got to add up to 1, so the other probability there will be 0.99, and then we have 0.2 for Regan, 0.2, and 0.3 for Michael. All right, and then so we can multiply along the branches to find the probability. So probability of A, it's the probability of A, and then this one here is actually the probability of B, it's the probability of a broken dish, given that A has happened. So that's the probability of B given A. Multiplying along the branches, we get the 3 of those. So what is the probability that at least one dish will be broken? So these 3 are the times when a dish will be broken, and so we can just add all of those together to get the probability of a dish breaking. All right, given that at least one dish is broken, what is the probability that the person washing was Michael? So we want to find the probability that Michael was washing, given that a dish is broken. All right, so that means we need the intersection of Michael breaking dishes divided by breaking dishes. All right, so we have the probability of broken dish from the previous question. And the intersection of Michael breaking dishes is this one here. So this is equal to 0.009 divided by 0.1. No, that's wrong. Back it up. Given that at least one dish is broken, what is the probability that the person washing was Michael? So we want to find the probability that it was Michael, given that a dish was broken. And so we need the probability of the intersection of Michael and breaking dishes divided by the probability of a broken dish. All right, so we have the probability of a broken dish from the question before, and the intersection of Michael breaking dishes is given by this branch of the tree diagram. Okay, so that means our answer is 0.009 divided by 0.019, the total chance of breaking a dish. All right, so 9 on 19.